All right, good evening, ladies and gentlemen. We're going to be carrying on today with the section that we did last time. And the section that we did last time is the section on voltaic cells. So I'm going to be looking specifically at voltaic cells. And last time in our lesson, we did a number of different things, and I'm going to try today to wrap it all up and bring it back together. Before we go any further, though, I have decided I need to work out what the theme is for today. Kayla and Jean, you're gonna have to help. It looks a party, clowns, minions. You're gonna have to help me. What is it?
We sort of have run out of ideas, to be quite honest, so we're open to suggestions. So we just sort of went for the general theme of hats.
Okay.
Yeah, so we just sort of went with that.
You're going to have to communicate to everybody else what the theme is, because otherwise we end up with two crazy, wonderful people. All right. All right. So let's go back to the actual work for today. So what I thought we'd do today to make it a little bit more concise, in our last lesson, sorry, I just need to make. Okay. In our last lesson, we looked at the general idea of how we get our oxidation numbers and then how we put them together. What I wanted to focus on today is actually making the cells. So I've tried something, I'm hoping it's going to work. I had a little bit of fun at the masterclass last night running two screens next to each other, and I found it really worked well for me. So I'm hoping today that my writing doesn't get too small for everybody to see, and that it does actually work bringing the ideas together. All right, please make sure that you mute yourself unless you've got a specific question. Otherwise, it disrupts the flow of the lesson. All right, so I'm going to share my screen. It'll hopefully pop up, yes, the way I want it to. All right, so what I've got here is I've got a typical setup of how your circuit might, well, how your cells might look, okay? Just quickly moving all of my bits to the right place so that I can see everything that I need to see. Fantastic. So I'm going to be picking on random examples today. So anyone who unfortunately missed the lesson on Tuesday, I think I did post it up just a little while ago, so hopefully you've managed to catch up enough. So we're going to randomly be looking at a couple of cells, and then we're going to look at what's the oxidation half reaction, what's the reduction half reaction, what's the net ionic equation, how do we do the cell notation, how do we work out the E-theta cell, and how do the bits of the cell fit together. I know this tends to be a little bit kind of routine in terms of this, but it's the best way to learn this quickly. All right, so let's say, for example, I set up a cell and I've got aluminium and aluminium 3+. So over here, my electrode is going to be aluminium, and the electrolyte must contain Al3+. Remember, an electrolyte is any solution that contains aluminium ions. So this, for example, could be aluminium chloride, or we could make it aluminium nitrate. I always tend to favor the nitrates because all nitrates are soluble, so you can never go wrong with the nitrate. Then I'm going to pick another half reaction, and please, I'm randomly picking these today. I haven't really even thought particularly about what we're going to do. I'm going to go for silver and silver plus, just because I feel like it. So that means that this electrode will be silver, and the electrolyte will be silver plus. Silver is an exception. You can't do silver nitrate. Silver can only be, sorry, you can't do silver chloride. You can only do silver nitrate. It's the only soluble silver salt. So, as we mentioned in the last lesson, in order for this reaction to be spontaneous, we must have the oxidation reaction on top and the reduction reaction at the bottom. All voltaic cells are spontaneous. They're all going to work this way. So my oxidation half reaction is at the top, and then my reduction half reaction is at the bottom. I'm also going to quickly fill in a little bit here, because with the oxidation half reaction, oxidation is loss of electrons, and anytime you read off this table from right to left, you will give off electrons, guaranteed. So that is my oxidation half reaction. Reading the other way is the reduction half reaction. So for this particular reaction, I can already write down here my OHR. You've got to read it the correct way around, and you cannot put in a reversible arrow anymore. So this will be Al goes to Al3 plus 3 electrons. What this physically means is at the electrode over here, aluminium will turn into aluminium 3 plus. When it does so, the size of the electrode will decrease in mass, because as soon as it's being oxidized, it's turning from a solid into an ion. As a rule here, anything on the table that doesn't have a charge, you can assume pretty safely is a solid. Okay, so that's the solid, that's the ion. So we know that this is aqueous and it dissolves in solution. With my reduction half reaction, is silver plus, picks up an electron and turns into solid silver. Once again, it doesn't have a charge, so we can assume it's solid. So what we'd observe here, and I don't really have a gray color, but I'm going to pretend that that is silver that I am depositing on top of the electrode. So this electrode here would increase in mass. Now, I touched on a lot of the ideas that I'm about to run through in the last lesson. Please, if I'm going too fast, you need to stop me and say, slow down, we're not following what you're doing. All right, so one of the ideas that I told you last time is anox and red cat. This means that the electrode where oxidation occurs is called the anode. So my anode was where aluminium is, so I can now go and comfortably call this the anode. And remember, it's also where the oxidation occurs. There also was red cat. Reduction is at the cathode. So I can now go across here and say that this is my cathode. So if I'm asked to name the anode or the cathode, I can say here that my anode, it's always got to be a solid, is aluminium, and my cathode is silver. Now, if we end up with an unusual situation, which we will, where you don't have a solid, for example, there's iron 2, I've got to go and quickly find it, iron 2 and iron 3, okay, let's go with chromium. Chromium 2 and chromium 3, both of those are charged, so they've got to be aqueous, they'll be dissolved in solution. If you don't have an electrode there, or if you're doing copper 2 and copper, or if you're doing iron 2 and iron 3 are somewhere in among here. I think I'm looking a little bit too low. Gosh, I can't find iron 2 and iron 3. Let's pretend that they're there. There's tin 4 and tin 2. But the point is, if you ever find, there's iron, I knew they were coming, iron 2 and iron 3. If you ever have any of those ones that I've just circled, they don't have a solid. The solid that you would therefore use is platinum. It's called an inert electrode, and basically you're sticking it in because you need a metal to be in the solution in order for it to carry electrons to or from the voltmeter, okay? So you always have to have an electrode. If you don't have a solid that's part of either of your half reactions, please remember you're going to use platinum. It's your only option. But we will be looking at examples like that just now. All right, so we've identified our oxidation half reaction, our reduction half reaction, our anode, our cathode. The next thing is which electrode has which charge. Now, you are more than welcome to learn the rule that in our voltaic cells, the anode is always negative and the cathode is always positive. Please remember when you do electrolytic, they swap around and they'll get the opposite polarity. Basically, you can think of this as when aluminium turns into aluminium 3 plus, it also gives off 3 electrons, so the 3 electrons leave. That means that the anode has an excess of electrons, which makes it negative. The electrons travel around to the positive, which is your cathode. So you may choose to memorize this, or you may choose to figure it out each time. I don't mind. All right. We touched very briefly on the fact that you've always got a salt bridge, that quite often you either have potassium nitrate or potassium chloride as the electrolyte in your salt bridge. And the function of the salt bridge, just to remind you, first of all, is to complete the circuit. And secondly, is to maintain electrical neutrality. All right. There are other things that you can put there, but they usually don't ask more than those two functions. The third function, if they're really desperate, is it allows you to keep the two half reactions separate. But I'm not going to put that down. All right. So that is pretty much, with one exception that I'm going to quickly fill in now, pretty much what we did in the last lesson. The last bit that I didn't look at is what is the oxidizing agent. I looked at that as well. And what is the reducing agent? Now, our rule here is the oxidizing agent is the substance that is reduced. The substance that is reduced is Ag+. The reducing agent is the substance that is oxidized, okay, which over here, sorry, let's get that right. It's still the same answer. It's a substance that is oxidized. So the answer is aluminium. Please remember that your anode and your cathode must be a solid, but your reducing and oxidizing agent must be the actual substances that are oxidized or reduced. And just an important thing here, they must be the starting material. You're not going to get away with saying that your oxidizing agent is Ag, because that's wrong. That's the product that we get from reduction. You can't say that it's your oxidizing agent. All right. Now what we're going to look at is what will the voltmeter reading be here. Now on your table, you will see that there are actually three separate equations that we can use to work out the E theta cell. And the E theta cell is the voltage of the cell under standard conditions. Those standard conditions are, I'm just quickly writing them here, standard conditions. I know I'm writing all over the place, just bear with me. The symbol that we use to show that they're standardized is actually that symbol over there, the theta, okay? And the standard conditions are that we must have a temperature of 25 degrees Celsius. If you wish, you may make it 298 Kelvin, it's the same thing. You must have a concentration for all electrolytes of 1 mole per decimeter cubed. And lastly, if you've got gases, the gases must have a pressure of 1 atmosphere. Now, I'm going to show you just now what it looks like and how we can manage to bring a gas into this equation, but it isn't on this picture, it's on my next picture. So the three equations that you're going to get, and I'm just quickly going to stick them down the side here, say E theta cell is equal to E theta cathode, got to get this right, minus E theta anode. These are on your formula sheets. You can always know that they're there. E theta cell equals E theta reduction minus E theta oxidation. Just bear with me writing across lines. And lastly, definitely going to write across lines here, E theta cell is equal to E theta oxidizing agent minus E theta reducing agent. Now, please note, all three of these are given, and it doesn't matter which one you use. I recommend the first one because it has fewer letters and it takes less time to write. It also, for me, is a cheat sheet, because if you ever forget which way around things go, you know that the cathode is where reduction occurs, and you also know that that's the oxidizing agent, because they're all the same thing. You also know that the anode is where oxidation occurs, and it's the reducing agent. So if you're smart, you actually use your formula sheet here as a bit of a cheat sheet to help you. Now, there's also an easier way. Your reduction half reaction is always going to be the bottom value. So although I'll write one of these, the method that I actually apply is always going bottom value minus top value. So therefore, I would say here that the E theta cell, which is the voltage or the reading that I'd get, the potential difference, let's be fancy, that I'd get when I set up the cell, and that E theta value will always be the bottom number minus, I've got to make sure I get the right one, the top number. So here I can say my cell potential is the E theta cell, let's get this right, is going to be the E theta cathode minus E theta anode. At the cathode, it's going to be positive 0.80, and at the anode, it's going to be negative 1.66. So if I put those together and I work them out, please remember that the negative becomes a positive. It's 0.8 plus 1.66 gives me an answer of 2.46 volts. And that tells me that if I connect up this cell, I will get a voltmeter reading of 2.46 volts. All right, I'm going to quickly ask a question just because I want to check that everybody's still here. Which cell would you set up if you wanted to get the maximum possible voltage? Any input from anybody? Which two half reactions would you use? Anyone? Okay, yeah, we got a taker. All right, lithium and fluorine. You would effectively make sure that you had the very top one here on the table and the very bottom one on the table, because that would give you the maximum possible voltage you could get. Now, why do you think we don't make all of our batteries lithium fluoride batteries? Why don't we use those two? We've got to be smart. Most of our batteries are zinc, cadmium, or some combination of those. Any ideas? You've got to be a bit practical about this when it comes to science. Okay, I'm just quickly waiting. Oh, we do have a volunteer. Fantastic. Let me go and find you. Okay, fluorine's particularly reactive, and also it may come in with a cost factor. So it may be a case that it's not as safe, or that it's too expensive to make or too dangerous to use. Whatever it is, there's an economic reason that we wouldn't do it. Now, hopefully at this point, all of you are comfortable if I give you a really easy, randomly chosen example to work out the oxidation half reaction, the reduction half reaction, to identify the anode, the cathode, the oxidizing agent, the reducing agent, and hopefully to work out the E theta cell. What we haven't yet done is something called the cell notation. And in order to do the cell notation, I'm going to unfortunately quickly have to clear quite a large amount of my writing. That's probably too much of my writing. Let me just delete a little bit there. I apologize for taking all of this away, but I need to. Okay. So there's a very easy way to write your half cells. Now, it looks hard when I write it this way. Breathe in, breathe out. This is a lot easier when I show you. So you're always going to have anode / electrolyte / electrolyte / cathode, which looks super complicated. But if I instead said to you, write down this guy, then this guy, then this guy, then this guy, in the order that you see them in the C, it gets a lot easier. So your anode is always going to be the first one that you read, aluminium. In order to be accurate here, we must put in the state that it's in, because it's an anode, it has to be a solid. The / here tells us that there is a change of state or a change of phase. We are going from a solid to an aqueous, so that's a /. Then over here, we write aluminium 3+, and it's aqueous. If we're going to be 100% good, we're going to remember that we're doing standard conditions. So we would also write here 1 mole per decimeter cubed. Okay, in fact, I usually write aqueous, 1 mole per decimeter cubed. But there isn't quite enough space, and they usually don't penalize you if you leave it off. The / represents the salt bridge. Please, me giving the explanation of what these symbols are for is important. They often ask it. Then on the other side, so I went that one. I'm not going to write out the AG. So it's going to be AG+. It's also aqueous. I'm being very good. I also write in here 1 mole per decimeter cubed. Okay. And then we do / because we're going from an aqueous to a solid, and it's just AG solid. This over here is called your cell notation. And in almost every single voltaic cell electrochemistry question, they will ask you to work out your E theta cell or they'll give it to you and make you use it. And they'll either give you the cell notation or ask you to do it. So you must be prepared to write it, but it's not as hard as it looks, even if you're trying to write it this way. This is the anode, this is the cathode, these are the two electrolytes. There is a change of state, there is a change of state, and there is a salt bridge. Now I'm going to teach you the fancy bits. If we don't have a change of state, for example, this is aqueous and this is aqueous, technically we don't put in a forward slash, we put in a comma. However, not all students are taught this. This is more of a university level thing. So if you put in a forward slash, they will never penalize you. But if you want to be technically correct, and if you're planning on doing chemistry at university, you put in a comma between two things that are in the same state. Also, if we have that inert electrode that I was talking to you about earlier, your inert electrode, remember, is where you don't have a solid, so you're going to put in platinum instead. With that inert electrode being platinum, you must write it on either the very beginning or the very end, depending on if it's your anode or your cathode. It is possible that we give you one that has an anode and a cathode that are both platinum, so they're two inert electrodes, but it really is a bit of an extreme example. All right. So ladies and gentlemen, I'm going to quickly ask you to take any screenshots of anything that you need here, and then I'm going to quickly stop sharing for just a second. All right. Can I ask just quickly, I know that I raced through this quite quickly on the Tuesday session, who's found that this has already kind of condensed it and made a lot more sense of how all the bits fit together? Thumbs up if that's the case. Okay. I was aiming very much to try and hopefully bring it back so that I didn't lose everybody, because I felt at the end of last week's lesson, it was, not last week, Tuesday's lesson, it was good, but especially with the sound cutting out, I got very concerned that it didn't fit well. All right, so the cathode and the anode must both be solids. If you don't have a solid, you have to instead use an inert electrode. So I mentioned to you that there was an option of an inert electrode. Here's an example. So I've once again left this nice and blank so that I can put in whatever else I want to here. But let's say, for example, we have a gas. Any gas that we put in has to have a special container that pushes the gas down below the liquid level so that it reacts with whatever's in solution. So how do you know if something's a gas? Good news, they tell you. There's a gas, there's a gas, there's a gas, there's a gas, there's a gas. Anything where there's a gas, you're very lucky. They make it very obvious for you that it's a gas. So you don't have to worry too much about what's a gas. So I've got an example here where this is a gas and this could be any other half cell. I did actually try, I was playing with this template, trying to mirror it on itself so that I could put in two gases at the same time and be extreme, but we really don't usually do that. They're not going to be trying to push their luck too much with making you stress. So I'm going to make this be chlorine and chloride. So I'm going to tell you that this is Cl2 gas and this is Cl minus. Now, because we don't have tons of time today, I'm actually going to do a reaction where we have two inert electrons. Actually, I'll do one with just one and then I'll do one just now with two. I'll not stress us too much. So let's put in the other half. Let's do chromium and chromium 3+. Why not? So this is chromium and this is chromium 3+. Now, obviously in an exam, you don't get to randomly choose what the things are. You've got to very carefully read through the information. Quite often they'll give you a diagram like this, and you'd need to make sure if they said chromium that you chose the one with chromium 3+, because there are also ones with chromium 2+, and oh, there we go, chromium. There are all sorts of other ones that they might have put instead. So make sure you use the correct ones. If we now quickly try to do all of the things that we did in the previous example, we're going to say here that chromium is oxidized to chromium 3+, and that chlorine is reduced to chloride. Remember, the ide is the ion. So if I look at these two, this is my oxidation half reaction. Please, when you write it out as the oxidation half reaction, you cannot put in a double-sided arrow. It's got to be correct, and you read it from left to right. So it would be chromium goes to chromium 3+ plus 3 electrons. Okay. Our reduction half reaction would be the one at the bottom. So that would be Cl2 goes to, is that a question? Sorry, I missed that. Is that a question, somebody? Okay, just quickly muting anyone. So over here we have Cl2 picking up 2 electrons and going to 2 Cl minus. Okay, quick bunch of things. Oxidation half reaction means that chromium, which is a solid, is the anode. In the case here, we've got a gas and an aqueous solution. We know it's aqueous because of its minus charge. That means that in this case, I actually lied here, the chloride is not there. I need to move my chloride quickly. My chloride is there. It's in solution. So who can tell me what they think the electrode will be here? It can't be chlorine because it's a gas, and it can't be chloride because it's aqueous. So what are we going to use as our electrode? Anyone? Come on, I know somebody knows the answer. Okay, and the answer is platinum. All right, so we would use platinum here. Just something that I probably should mention at this point, please read the questions very carefully. Sometimes they might ask you, what is the name of the electrode? And then you'd have to write out platinum or chromium. And sometimes they ask you to write out the formula, in which case you've got to be very specific. If they ask you to write out the name of an ion, this would be chromium 3 ion, ION. You must write out the name, and usually I recommend if it's got a charge, write ion afterwards. So we have got our example here of where we've got a gas, we've got an aqueous solution, and we have to bring in platinum in order to make this happen. So my anode is chromium, but my cathode here is platinum. Next important thing, my anode is negatively charged. So my chromium anode is going to be negatively charged, and my platinum is going to be positively charged. Hence, the function here of the platinum is that it allows the reaction between a gas and an aqueous solution to take place, and it effectively conducts electrons to the external circuit. We've actually got to be careful. I shouldn't use the word to, it's from, because here the chromium turns into chromium 3+, and it gives off 3 electrons, which travel up, around, down, and to the chloride, well, to the platinum electrode. Okay, so just quickly, Tristan, the reason that platinum is the cathode is that if we don't have an electrode in the reduction half reaction, you can't have a gas carry electrons up to the voltmeter or carry electrons from the voltmeter down into the half cell. So, and you can't have the chloride ions do it. So if you don't have a solid, remember an electrode is a solid that conducts electricity. If you don't have that solid that conducts electricity, then you have to put in a solid. And the reason we put in platinum is that platinum is inert, and the word inert means unreactive. So the platinum is not going to react with anything in solution. In fact, platinum technically is on this table, but if you look at it, platinum is on the right-hand side, so the only way it can react is to be oxidized. But if you look at it, it's very far down the table, so it's an exceptionally poor reducing agent, and it's very unlikely that you would find anything that would allow it to be reduced by platinum. So platinum, because of that, will never be oxidized in this particular setup. So that's why we're able to use it, because it isn't going to react with anything else. We can safely assume that if there's anything below here which it might have reacted with, there will actually be a better reducing agent above it. So for example here, even though the platinum could reduce the chlorine to chloride, so even though I could technically have this reaction here happen, it won't happen because chromium, which we do have, is a better reducing agent. The increasing reducing ability says that this is a better reducing agent. Therefore, this will be selectively oxidized. If it's between platinum losing electrons and chromium losing electrons, chromium is going to be better at losing electrons, so it will selectively happen. All right, so that basically explains to you why the platinum isn't going to react. All right. Okay. All right, wonderful. So what I now want to do is one thing that I skipped off in the previous example, which is our net ionic. I forgot to cover the net ionic equation. We did it on Tuesday, so I assume it doesn't really matter too much that I left it off in the previous example, but I don't want to leave it off in both. And with our net ionic equation, the point is that we're describing the overall chemical equation that happens. So when you do your net ionic, step number one is making sure that we have the same number of electrons. We don't. We've got two being gained in the reduction half reaction and 3 being given off in the oxidation half reaction. The lowest common multiple of these two is 6, which means that everything in the oxidation half reaction must get multiplied by 2, and everything in the reduction half reaction must get multiplied by 3. I find that I then grab my pencil and I immediately go 2, 2, 6, and 3, 6. This is going to be 6. And then from there, my net ionic is everything before the arrow on both the oxidation and the reduction half reactions is written first. So it'll be 2Cr. Make sure that your C doesn't go lowercase. Mine nearly did. Plus 3Cl2. We don't bother writing in the plus 6 electrons because you're going to have them on the starting materials and the product, so they're going to cancel. And that goes to give us 2Cr3 plus 6Cl minus. And that over there is your net ionic equation. We're rather lucky. They've taken out the idea of using spectator ions. So it used to be a case, sorry, I'm just suddenly looking at this, it looks wrong, but it isn't. I was suddenly worrying because both of these, that's a solid and that's an aqueous, sorry, that's a solid, that's a gas, and both of these are aqueous, but it's okay. If we wished, we could group these two together and make it become chromium chloride, okay? That's a 3 plus and that's a minus. We could make it chromium chloride, and there are 2 of them, but we don't have to do that, okay? So you don't have to worry here with the electrons here and here, because we technically have had 6 electrons on this side and 6 electrons on this side, and we'd have canceled them both out. If you want, you can write them in when you do them and then cancel them out afterwards. But the point is, anything where there's the same on both sides, you're going to simplify with your net ionic equation. All right. I hope that answered the question that somebody just quickly posted. All right. So the 2 things that I now want us to do is to work out the Etheta cell and to work out the cell notation. I'm going to do the cell notation with you because it's different, but I'm then going to ask all of you at home to please do the last part to just check that you can do it. All right. All right, so a spectator ion, I covered the idea of a little bit in the last lesson on Tuesday. A spectator ion is a substance that's involved in a reaction that doesn't change its oxidation numbers. In this particular case, we didn't actually have any spectator ions because those would join together. So it's chromium and chlorine going to form chromium chloride. There weren't any, but sometimes you do get complicated parts of an equation when you bring in other things, like, for example, where there's sulfur dioxide and water being formed, and then the hydrogen doesn't change oxidation numbers. So if we look here, that hydrogen is +1, that hydrogen is still +1. So the hydrogen's function there was to act as a positive ion to hang out with a negative ion. So sometimes we have substances that don't change oxidation numbers. Because this is called the net ionic equation, it usually leaves out those substances. All right. Okay, so what I wanted to just quickly do with you is how we would write the cell notation. So this is the example I did just briefly on the previous page, but now we've got something that's slightly different. But I'm going to start with everything the same before I add on the different. So we start over here and we write chromium solid. Then we write / because there's a change of state from solid to aqueous. And it's chromium 3 plus aqueous, And we write in here, comma, 1 mole per decimeter cubed. I'm going to write a little and maybe it'll all fit. Double / salt bridge. Then I write Cl2 gas / 2Cl minus. Please note, it doesn't actually matter if you leave off that 2. If you just make it Cl minus, that 2 is optional. Then it'll be aqueous 1 mole per decimeter cubed. I'm writing very small here because I need to fit it in. But the problem is, although I started on the anode, I don't finish on a cathode. But I do know that my cathode is platinum. So what I do right at the end, and please note you mustn't have these 2 underlining bits, that's just me emphasizing it, is that right at the end we then write / because there's a change of state between these two, platinum and solid. Okay, I'm hoping that you all can see the little bits on the end. So all that happens if we've got an inert electrode for our cell notation is we write platinum right on the end. All right. Can I quickly just ask, I'm going to pause share for just a second. Does that idea of how we deal with this make sense? Is everybody happy with how it fits together and what the point is of the inert electrode, first of all, and secondly, how we fit it in? Now, the inert electrode, please remember, is not doing anything else. The inert electrode is there. It's not going to change what the oxidation half reaction is or the reduction half reaction is. It's not going to change the fact that this over here is my reducing agent, because my reducing agent is oxidized. It's not going to change the fact that this is my oxidizing agent. So it doesn't suddenly become the oxidizing or reducing agent. The only thing that it will be is it will be one of my electrodes, and when I write my cell notation, I need to write it at the end. It is also not going to change the Etheta cell. Now, I'm going to make life easy. I'm going to remind you what the equation is, and I'm going to ask everybody here quickly if they can calculate for me, I'm just going to move that across, what they think the Etheta cell should be in this case. I'm going to try and squish it in the bottom. Okay, so I'm going to ask everybody, I told you I'd remind you first. So this is the Etheta cell. Etheta cell is equal to Etheta cathode minus Etheta anode, or Etheta reduction minus Etheta oxidation, or Etheta oxidizing agent minus Etheta reducing agent. One important thing, you may not abbreviate these even if you think it looks the same. So if I write Etheta cat minus Etheta an, I've lost that mark. If I write Etheta red minus Etheta ox, gone. If it doesn't look like the formulas that are on your formula sheet, you've lost that mark. So please don't be lazy. If you're going to be lazy, pick this one. It's got the fewest letters in it and use it. Okay, so I'm going to quickly pause while I write this out and give all of you an opportunity to hopefully fill in all the bits. Please make sure that you're also aware of what your units need to be. All right, when you're done with that, please give me a thumbs up so that I know you've got to an answer. Okay, well done. Okay, good. Okay. Checking the question. Yay! And someone's even given us the answer. All right. So if I now share this, there's the answer. It's 2,1 volts. All right. Ladies and gentlemen, is this beginning to make a little bit more sense as to how we put the bits together, what they mean, and all of the, I guess, the fundamental building blocks that build up this section? In order to be sure that you have the theoretical knowledge, you need to know the following things. I'm just going to quickly stop sharing. I know it's going to clear everything. So please make sure you've got all the bits you wanted from this. There's one last thing I didn't fill in here. Sometimes this is one of their favorite silly, easy questions. They'll go, what is represented by the letter Q or P or any letter? That over there is your salt bridge. They may then ask you, what is the function of it? It is to complete the circuit, to maintain electrical neutrality, or to allow the two half reactions to be kept separate. They may ask you, what is the function of this particular electrode or platinum in this reaction? You'd say its function is an inert electrode, which means that it's there to carry electrons to and from the external circuit. Sometimes they leave this bit blank and they ask you, what is that? And you need to say it's a voltmeter. And typically the reason we use a voltmeter is it's to measure the cell potential. Okay, please be very careful when answering questions about the difference between giving them the net ionic equation if they look for it, the cell notation if they look for it, or the cell potential if they look for it. If you give them something that they haven't asked for, even if it's correct, they're unfortunately not going to think you're very impressive because you happen to get it right. Okay, so I'm just quickly going to stop sharing. I'm going to double check, is everybody happy with what we've done so far? Because what I thought we'd finish off with today, I'm unfortunately not going to get to the kind of past paper questions. Those will be done in the masterclass. And I had a very special request for this week because a lot of you haven't yet done redox. Somebody commented that between Thursday, today, and Sunday isn't really a long time to get decent mastery. So they requested if it was possible that the deadline for when you can make the masterclass is pushed back a little bit. And I think what I'm going to do is, you already know that if you get 80% mastery, you're in that masterclass. So I'm going to push the deadline back to just before our lesson next week, Tuesday, so you get slightly longer to try and figure out what you need to figure out if you do. If you make it into that masterclass, in that masterclass, we're only going to be doing past paper questions, so you'll have a good opportunity, I guess, to flesh out a lot of the rest of the things. Can I ask just a quick question? Who here watches the masterclass videos even if they don't make it into the masterclass? I just want to know whether they're being watched or whether it's a case of they're not. Okay, because generally with those we tend to go into past paper questions. All right, so they are available there for you. I can tell you that I do think there's a benefit to be there first. I think quite often, I find at least, I pay more attention if something's happening live than if it's on a video. I tend to zone out in videos, but I hope all of you aren't quite the same. All right, so we're now going to go back and we're going to do one last example. But with this last example, I'm going to ask you questions, give you a chance to answer, and we'll check if you've got all of your ideas. Please be warned, since we've done a couple of these already, it's not going to be the easiest example. So let's get started. I'm going to write the substances here, but I'm not going to tell you where the half reactions are. You've got to find those for me as well. Okay, so I'm going to tell you that in solution, we have Cr3 plus and Cr2 plus. Okay, sneaky. I'm going to be super nice here because I don't have to. Who can already tell me what electrode this has to be? I'm giving you a hint, it's not chromium. What electrode does this have to be? Anyone? We've got Cr3 plus and Cr2 plus, they're both aqueous, so this has to be our platinum electrode. Sometimes they're nice and they remind you, sometimes they ask you. Over here, this has to be a gas. So I'm in fact going to pick a bit of a weird one. I'm going to pick our value here. I shouldn't have told you that. I'm not going to pick the value here. I've changed my mind. But I'm going to quickly point out to you the value here. You'll notice that hydrogen has got a value of 0. That is because it is what we call the reference electrode. In order for it to act as a reference electrode, every other substance's Etheta cell potential is determined by trying to oxidize or reduce hydrogen, and they figure out how large a voltage they get, which is why hydrogen as the reference is 0. I'm not using hydrogen now though, So sorry, changed my mind there. Okay, I deliberately didn't want to tell you what the two half reactions were. So I'm now going to go and try and find another one to do. Oh, and it's going to make my life hard trying to find another one to do. All right, I've changed my mind. I'm still going to go with it. You're just going to have to find the equation again. Okay, so here we had H plus. All right, so I'm not telling you we've got hydrogen, we've got H plus. I'm going to put a giant question mark here, and we're going to start. First of all, who can tell me what I should have put instead of the giant question mark? You're welcome to unmute yourself and shout, or you're welcome to chat. I don't mind which way you tell me the answer. So instead of the giant question mark, what would be the name of this substance that's there? Anyone? 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 I feel like I'm waiting by the phone and no one's answering or calling. Okay, yay, we have a taker, and it is platinum. Inert, please, it's not invert, it's inert electrode. Inert, I-N-E-R-T. Inert, like sometimes we call our noble gases inert gases. Interesting fact if you didn't know. So over here, this is going to be platinum because it is the inert electrode. And the reason we needed to put in platinum is that hydrogen is a gas. And H plus, in fact, sometimes we don't even tell you it's H plus. H plus comes about because we put an acid in here. All right, my next questions. Who can tell me, if this is going to be using the table properly, what is the pressure of the hydrogen gas? These are the kind of questions that they're going to be throwing at you. You need to be ready for them. What is the pressure of the hydrogen gas? Anyone? So if I now want to know what is the pressure, I've got a little valve and I'm trying to regulate it. It's 1 atmosphere. Fantastic. Just for anybody who doesn't know, 1 atmosphere is 101,3 kilopascals. If you did gases last year, you probably remember that. Next question, what is the concentration of this acid in my solution? Bearing in mind that I'm going to make it a monoprotic acid. I'm going to be nice. It's a monoprotic acid. What is its concentration? And the answer is 1 mole per decimeter cubed. Good. Those are our standard conditions. The last one would obviously be that this must happen at 25 degrees Celsius or 298 Kelvin. Interesting question. If I used sulfuric acid and we assumed that it was if we use sulfuric acid and we assume that it's a perfect strong acid, I may get away with using a different concentration. What concentration of sulfuric acid should I use? This is us being very technical. The sulfuric acid, you could actually get away with using 0.5 mole per decimeter cubed, 0.5 moles per decimeter cubed, for the simple reason that then the concentration of the H plus, which would join with water to form H3O plus, we're jumping into acids and bases a bit here, that would be 1/2 as much. So technically, when we're talking about the concentration, it's the concentration of the ions in solution, not necessarily of the substances that make up the ions. All right, can I ask all of you right now for me, can you please write out the oxidation half reaction and the reduction half reaction? I'm going to pause for just a second while I do the same, and then I'll check where everybody's up to and check whether you've got those ideas correctly. All right, so quickly get started on that. All right, if you're done with that, quickly give me a thumbs up. If I'm going too fast, please also let me know. I'm going to wait till at least a couple of you have given me a thumbs up. Okay, is there a question? Mara, you're right. Okay, so just one final reminder, I've had the person re-remind me that the cutoff for the master class will be later than usual. All right, so it'll be just before the lesson. Okay. All right, ladies and gentlemen, because we've only got a few minutes left and I want to actually get through quite a large amount of this, I'm going to be naughty and give you the answer. So for your oxidation half reaction, you should have chromium 2 plus going to chromium 3 plus, and you'd write it out like that. Please be very careful. It isn't going to gain or lose more than one electron. It's only one from the 2 plus to the 3 plus. And over here, my reduction half reaction is H plus, picking up 2 electrons to form H2. All right. My next question that I want to know here is which... Okay, so Rebecca, sorry, how did I determine my OHR and my RHR? I went here and I saw chromium 2 plus and chromium 3 plus. So there's the 2 plus and there's the 3 plus. I circled both of them. Then I went and found my H plus and my H2. My platinum in this case is not part of the reaction. It's an inert electrode. So I circle the H plus and the H2. Once I've got all of them circled, that means that I can read each half reaction either way, oxidation or reduction. I can choose. Because in order to get a spontaneous reaction, you need your oxidation half reaction above your reduction half reaction. This will be read in that particular order. For all of voltaic cells, it's going to go that way around, no exceptions. There is a reason for it. And the reason is that the substances, if you look here, increasing reducing ability, the substances on the top, on the right-hand side, are going to be better reducing agents, which means that therefore they will be oxidized easily or oxidized selectively. Okay. If you read here, it says increasing oxidizing agent, says that the substances down at the bottom on the left-hand side are stronger oxidizing agents. Therefore, they are reduced selectively. Selectively means that a lot of things could be oxidized or reduced, but they're the ones that are chosen. So these are reduced selectively. All right, I did see that there was a chat comment there. All right, and this would be, okay, so I just had a question. Is this a spontaneous reaction? All of voltaic cells, which is the only bit of it that I've looked at, is spontaneous. So voltaic cells spontaneously reacts and turns chemical potential energy into electrical energy. So basically, we're taking a substance that wants to lose electrons and a substance that wants to gain electrons, and we're allowing them to do what they want to. But we're being sneaky. The substance that wants to lose electrons, which in this case is chromium, can lose its electrons, but in order for the electrons to be lost and to move through to the substance that wants to gain them, which is the hydrogen ions in solution, we make those electrons run through an external circuit for us, and in the process, they do work. So we turn chemical energy into electrical energy by having a spontaneous reaction, but forcing the electrons to go through an external path. One of the reasons why we keep the two half cells separate is because if we just dunked all of this in solution, the reactions would happen, the electrons would get transferred, but we wouldn't be able to actually get any benefit from the electrons being transferred. Just quickly writing in here that this is a salt bridge because I'd left that off. All right, so that's our oxidation half reaction and our reduction half reaction. Who can tell me the name of the anode? In fact, this one's a bit of a cheat one. Who can tell me the name of the anode anyway? Anyone who knows what the anode is? Okay, the anode, and this is why it's a bit of a cheat one, is it's platinum. The question though is which platinum? Oxidation half reaction gives us the anode. The Oxidation is with chromium and chromium 2 plus. So this platinum is the anode, and the anode is negatively charged. This is my reduction half reaction. So this would be anode on that side, and then this would be where the cathode is. Please note, neither of these have a solid, so they're not anodes or cathodes. Here, this platinum is my cathode, and the anode is negative, the cathode is positive. All right. Can I ask, who knows what the oxidizing agent is? They'd usually say write down the name or the formula of the oxidizing agent. Which one is the oxidizing agent? Okay. H plus. Good. Please be careful. It isn't H2. It's got to be the starting material. Okay, so it's got to be whatever's written before the arrow. So this over here is my oxidizing agent. I cannot just pick anything from the reduction half reaction. It's got to be the starting material. Who can tell me what my reducing agent is?
Is it C3 plus, man?
Careful, it's going to be this side. It's got to be the thing we start with. So it's the 2 plus. So the 2 plus is the reducing agent. Okay, so you are on the right half reaction, but you've got to remember it's not the product. It's the thing that you start with that way or the thing that you start with that way. Those are the only substances. Just something for interest's sake, because I'm going to make sure I cover it well. But sometimes we call the oxidizing agent the oxidant and the reducing agent the reductant. But it's not often something that gets asked in a matric exam. I haven't seen it for a very long time, so it's just worth mentioning it. All right. I'd like everybody, as a challenge now, we've got 2 last things to do before the end of the lesson today. I'd like everybody to try and write down the cell notation for this cell, bearing in mind that you've got your inert electrodes. So I'm going to quickly pause sharing. I'm going to give you a chance to write down your answer, and then we're going to check. I'm going to write down the full answer with all of the bells and whistles. Please do likewise. You don't have to put in the conditions, just put in the states. If you want to, and you remember what I told you about when they're in the same state, you may show off and be fancy. But you got to be careful that you're not fancy when it's wrong. Okay, please note, I asked you for the cell notation. That means I need to see forward slashes for Saltbridge and single forward slashes for things. I don't want the reaction. If you're giving me the reaction, you're giving me the net ionic equation. That isn't what I want here. I want the cell notation. You've got to make sure that in an exam, you're paying attention to which thing they're asking you for. All right. Okay, I'm going to quickly check. Don't worry. It's a common mistake. So the person who made the error actually has apologized. Please don't worry. I don't mind if you do it now. I don't want you to do it in your final exam. It's one of those things where it's painful as a teacher when you watch somebody have written down the perfectly correct wrong answer. So they've gone and done everything correct, but not for the right substance. And you almost want to cry because you know that they were so excited that they could do it and they didn't realize they messed it up. Probably until they walked out of the exams and then their friends told them that they had, but that's just mean. All right. Is there anyone who needs me to wait a little bit longer for them? Or are you all good to see the answer? Okay. So I'm going to resume sharing. My answer, and please ignore the platinums on either end, goes chromium 2 plus, chromium 3 plus, 2H plus, and H2. If you left off that 2 there, it's still correct. And if you put a / here instead of a comma, it's still correct. You remember the comma here says that they are the same state. So they're both over here aqueous, state or phase. That represents a change of state. That's our salt bridge. Change of state again. Please rather put in / if you're not certain, because if you put in a comma here, you'd have been wrong. So you've got to be very careful that if you're going to be fancy, you're fancy and right, not fancy and talking nonsense. All right, ladies and gentlemen, I know we're about to go a little bit over time, but I think I'd rather give you the opportunity very quickly to work out the E theta cell. Remember, it's E theta cathode minus E theta anode. So I'm going to pause one last time, give you a chance to do it, and then we're going to go over it in just a second. Okay, did somebody raise a hand? If you did,
Yeah,
you're welcome.
do you
Yes?
have to put the solid and the aqueous in brackets and stuff? Do you have to do that?
Do you know what? I'm going to tell you yes. There are cases where they don't penalize you if you leave it off, but the problem is I don't know if that's going to be the case or not. So I would rather not tell you that you can leave it off and then have you lose a mark. It's very silly to lose a mark for something you know you should be doing just because you're in a hurry or because you think you can get away with it. So I'd rather caution you against it and say don't do that. Put in the states.
Okay.
You can often get away without putting in the conditions. Like the most recent sets of exams that we've marked, they don't get fussy about it. But the point is that they don't tell you before they change the rules. So I find that if you are lazy or slack and they change the rules, it counts against you. None of the rules are ever changed in a way that would disadvantage someone who's got it perfectly right. So it's only going to be a case of if you're cutting corners that suddenly they change the rule and that corner is one you can't cut anymore, and then you lose marks. All right.
Okay.
I think I've got some answers here. All right. So the answer, yes, the person who's given the answer here is in fact correct. It's 0.41 volts. All right. Okay. Just something to make a note of. If we are dealing with our voltaic cells, remember, they're always spontaneous and they always turn I keep saying that, they always turn chemical energy into electrical energy. Voltaic cells will always have a positive E theta cell. They've got to be spontaneous. The thing that's being oxidized must be the substance that's a better reducing agent, and the thing that's being reduced must be the substance that's a better oxidizing agent. Now, there was two last questions. Somebody had asked if I could quickly do the net ionic, so I'm going to do that. But if you've got another question, quickly ask it as well. Okay, Tristan, what's your question?
No, I left my hand up, sorry.
Okay, don't worry. Any other questions? Or is it just the doing the net ionic? Okay. So yes?
I was wondering how much info will they give you to determine which half reaction to use from the table? Especially
they will give you enough information to make it non-ambiguous. So sometimes if you don't read it carefully, you mess up a lot. But they usually will give you, so for example, I may not have told you that this was H+, but I may have told you that this is hydrogen and this is HCl. And you need to be smart enough to realize that's H+. Sometimes I may tell you that this is zinc sulfate and that this is zinc, and you'd need to look at it and go, well, we've got zinc and zinc 2+. So they've got to give you enough information that you can't be getting confused about what the substances are, and there can't be two right answers, but that's about it. If you go and look at the past papers, you'll usually see that you're very lucky if you get it this way around. In fact, quite often they give it to you backwards, but we're going to hopefully be dealing with those situations in the masterclass. If you work towards that or watch the video, you'll have a chance to see the kind of how much information you get. There's a question here, will there ever be a situation where the E theta cell is negative? Yes, there will. but that will fall under our electrolytic cells, which I'm only going to do in a later lesson. So electrochemical cells, if you look at the video from Tuesday, electrochemical cells is voltaic, which is all I've done today, and electrolytic, which I'll be doing at another stage. Technically, everything from today is question 8 in your chemistry paper, and your electrolytic cells is question 9. So they're linked, but, well, they're opposites of each other, but they're not, I'm not able to cover them both together in one go. It's too much. All right, so if we go to this example, we have got an electron there and 2 electrons there, so I times this by 2 at the top. I don't have to times this by 2. The lowest multiple will then be 2. So I'll put a 2 there, 2 there, 2 there. I'll then write out everything before the arrow, except for the electrons. As long as they're the same, I can cancel them all off. So it'll be 2Cr2 plus 2H plus goes to give you 2Cr3 plus H2. And that is your overall reaction. You could be good and put in aqueous and aqueous and aqueous and gas. And sometimes that will be required and sometimes it won't. All right. Have I managed to answer all of the different questions that people have asked or that needed assistance with? I know that this section can be a little bit scary. Can I just quickly stop sharing? Okay. Okay, someone else has got a question? Yes, quickly.
Ma'am, like in general, do you think that platinum is like a common inert?
It's the only one you need to memorize. It is possible for us to use graphite as well as an inert electrode, but platinum is the one that they're going to use. We teach our students, if you don't have a solid, because you've got a gas and an aqueous or 2 aqueuses, stick in platinum, it's safe.
Okay, cool, thanks.
Any other questions? All right, so with this particular section, I'm hoping, I know it's very fresh for some of you. Some of you have probably never done it at school. Hopefully you'll find that when you do it at school, it links in and meshes a bit better. I find that at this point in the year, we're just aiming to make sure that everybody has an understanding or a basic understanding of what they need to do. So if we're doing this where I've taught it to you first and your teacher teaches it to you afterwards, you may find that it still lays a better foundation so that when they're explaining ideas, you're linking it to a bit of knowledge that you've already built. Okay, so please, if you have any questions as you work through the examples, do let me know. And I strongly recommend that you go and practice this on Siavula. But please remember, it's only the voltaic cells. If you try to do electrolytic, you're going to go crazy. All right, Rebecca, what's your last question? All right, I'm not quite certain.
Sorry.
Yeah, don't worry. All right, have an absolutely lovely evening, everybody.